These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you. What are the transition elements?
In a D block.
That's right.
Elements are in D block.
And where's the D block in the periodic table?
Like right in the center.
Right. So the transition elements are the elements that are in the D block, and those are generally those are metals. By the way, which block is this?
S.
And which block is this?
P. F.
Now, which D block is this one? 1D, 2D, 3D, 4D? Which D block is this one?
Oh, it's 3D.
3D, that's right. And then this would be 4D. So here's something that's interesting. There is no 1D or 2D. The first D block is the third. For that matter, which P block is this?
That one is 2B.
Right? And which F block is this?
It's like 5 or 6. It's between, it starts like between 5th and 6th row. So it's...
Now, so I think you're answering a different question than I was asking. You're answering which of these rows first has an F block. But what we need to know is what number goes with this F block. For example, even though this is in the 4th row, 1, 2, 3, 4, it doesn't have the number 4. It's still 3D. So what is the first F block? Is the first F block 1F, or 2F, or 3F, or 4F, or 5F? Do you know where the F block first shows up? Well, there's a straightforward pattern. By the way, which block is this?
1.
Yeah, 1S.
S.
So if you think about, so what we're talking about here are the different types of orbitals, or subshells. And here are the basic types, S, P, D, or F. So notice that the first type is called S, and that first appears with a principal quantum number of 1. And the second type is P, and that first appears with a principal quantum number of 2. There is no 1P. Now the third type of subshell here is D, and that first appears in the third quantum number. So you can see the pattern here. This first appears in 1, this first appears in 2, this first appears in 3. So based on that pattern, what number should this first F block get?
5.
I don't think so. Pardon?
4.
4, right, because it's the 4th, right? It's the 4th in this series.
Oh, that makes sense.
So that's a way that makes it easier. This is just this is not an explanation. It's just a memory aid to remember what the first number is. S is the first of these types of orbitals, and it also first appears with principal quantum number 1. P is the second type, and it first appears with principal quantum number 2. D is the third type, and it first appears with number 3. And F is the 4th type, and as a memory aid, that first appears with number 4. You can't just, now you might remember that this first appears, so this is like element 57, and this is like element 58. So the F block first appears in this row of the periodic table, so to speak, but this is not the 4th row of the periodic table. It's the 1, 2, 3, 4, 5, 6th row. So you can't use this row to figure out what this number is over here. But now we have a memory aid for figuring out what this is. So there is no 1F, 2F, or 3F. You first have a 4F, and then which block would this be?
5F.
5F. So the hard part is remembering what the first number is. Then it's easy to get the remaining numbers. For example, what number is this? What block is this?
5D.
5D. So notice that the 4F is in the same row as the 5D. That's the thing that makes things confusing. You can have different principal quantum numbers in the same row of the periodic table once you get further on down. So when you're doing these types of problems, it's helpful to take your periodic table and label the key blocks so you don't have to keep figuring them out over and over. Because if you're in a hurry, it's easy to make a mistake when you try to figure out what the number for a block is. But if you write them all down carefully at the start, then you can just refer to those. For that matter, then, what block would this be?
It's a 5S. Oh, no, it's a 4s. No, 6s. 6s, because it goes
1, 2, 3, 4, 5, 6s. That's right. And how about this over here?
6b.
Okay, so as I was just saying, it's easy if you're in a hurry to make mistakes when you're putting in those numbers. So notice that in this one row, we have the number 6 for the S and the P blocks, we have the number 5 for the D block, and we have the number 4 for the F block. Now, they couldn't actually fit this in the table because it would make the table so huge. So in desperation, they kind of put it down here as a footnote. But you could have just crammed this into the table over here, and then you would have 1, 2, 3 different principal quantum numbers in the same row of the periodic table. So the safest thing is just to label all of these. Okay. Well, one thing that you need to be able to do in the course is write electron configurations. So for example, let's try writing the electron configuration for neutral titanium. The electron configuration for neutral titanium. Do you know how to do that, or should we go through that together?
Oh.
Can we go through that? It's been a
Okay.
while.
Okay.
Oh, yeah.
And of course, you'll need your periodic table. Yeah.
Yeah.
So I should
Yeah.
do that. Okay. So let's find titanium in the periodic table.
On a 3D. In a 3D setting.
Good. So here we have titanium. We're going to write the electron configuration. Now, generally speaking, how many electrons does neutral titanium have? How many electrons would a neutral titanium have?
27 minus 22.
Actually, just 22.
22.
A neutral titanium would have 22 electrons because it's the 22nd element.
Okay.
So since it has an atomic number of 22, it must have 22 protons. So to be neutral, it would have to have 22 electrons.
22.
So it would have 22 electrons. However, most of those are core electrons, which we don't care very much about in chemistry. Chemical reactions are determined by the valence, the outer electrons, not the core electrons. So most of those core electrons we don't care about very much, and usually we don't bother writing out their electron configuration in full detail. We would simply say that the core electrons are represented by the electron configuration that argon would have.
Oh, right.
Does it make sense that we would use argon for that? All right. So we would simply say that the core electrons have an argon-like configuration because argon is in this position on the periodic table. And we're just going to focus on the valence electrons. That's what it looked like your instructor was doing in lecture.
Yeah.
Now, how many valence electrons does titanium have? How many valence electrons does it have? We can tell from the periodic table how many valence electrons a neutral titanium has.
2.
Now, the number of valence electrons is the number of columns that is from the left. And I actually think titanium is in the 4th column.
4.
Oh, okay.
Right? 1, 2, 3, 4. After all, if these are the core electrons, then this, and this represent the extra electrons. So here we've got the core, and these must be the extra outer valence electrons. So neutral titanium has 4 valence electrons.
So it's going to be 4s to 3d4. No, 3d2 because it's 4.
Yes.
Yeah, we have total.
Okay, that's right.
Okay.
So this would be the valence electron configurations. All right, so that's one of the skills that your instructor went over, and we'll need that for more complicated problems too. So it's important to be able to get the valence electron structure. Now, the nice thing is notice that you can use the periodic table to get the valence electron structure. One thing that's interesting here is notice that in a neutral element, who fills up first, 4s or 3d?
D.
In a neutral element, who fills up first, 4s or 3d? Actually, the 4s got filled up first, right? After all, if the 3d was filling up first, you would have put all 4 in the d block. How many electrons can the d block hold in total?
10.
Yeah, how do you know that? Because there's 10 columns. If you look at the periodic table, there's 10 columns there, but we didn't do this. First, we put the electrons in the 4s block. Now, how would you know to do that? Well, the nice thing is you can just read it off the periodic table. The periodic table tells you what order to put the electrons in for neutral elements. The periodic table here told us that 4s comes before 3d, so we don't need to have that memorized. The only thing that we had to know is we had to know this was the 3D block rather than the 4D, say. That's why I said you should start by labeling the key blocks so you don't get confused about this. And you had to know this was the 4S. But once you know that, the table tells you that 4S comes before 3D. So we know that this was not the correct way to do the neutral titanium.